So the next protocol is called a selective repeat protocol, often written in short as SR, right? This is also a sliding window protocol. Just like your go back N. But as the name says, look at this, selective repeat, which means in go back N, what do? Whenever we have a problem, we go back. Look at this example that I showed you earlier, right? So here we had a problem. My frame 2 was lost, right? In go back N, frame 2 was lost. I would go back and resend all the frames in the window if required, right? That's what go back N does. I just keep resending all the frames that in the whole window, thereby wasting lot of time here actually. So selective repeat, on the other hand, what it says here is, let us only selectively repeat sending those frames which are actually lost or which are corrupted, right? To achieve this, as the name says, selective repeat, which means I'm only repeat selective frames which I know haven't reached the receiver or which have been corrupted in the process of being sent to the receiver. So the idea here is as follows. Okay. So the first concept here is you have a sender window. You have a sender window whose width or whose length is greater than 1, right? It has to be strictly greater than 1. Similarly, you have a receiver window. Look at this. In your go back N, if you recall your go back N, we had a sender window and you had a receiver window. The receiver window was always size 1. Look at this. The receiver window, I wrote this somewhere. Yeah, the receiver window is always of size 1. But in the case of selective repeat, my receiver window is the same size as my sender window. And both of them have to be strictly greater than 1. This is very important, right? And let me tell you a couple of quick concepts, then we'll go into the diagrams and understand it better. The next key idea here is, if you want to resend any frame or retransmit any frame, resending is also called as retransmission. If you want to resend any frame, how does it work? Imagine I sent a frame. There are two basic ways to ensure resending of frames which have been corrupted or which have been missing and things like that. Okay, there are two broad ideas. One is called implicit, the other is called explicit retransmission. In the concept of implicit retransmission, you have your sender, you have your receiver, right? In the concept of implicit retransmission, what happens is the sender sends something. Let's assume I send frame 0. The receiver always sends an acknowledgement back. The receiver always says acknowledge 1. So the receiver always sends an acknowledgement for every good packet received. Look at the keyword here. For every good packet that it has received, it sends an acknowledgement. Remember, it is sending for each good packet. So this is no more accumulative. Remember, this is not accumulative. So let me accumulative, right? This is not accumulative acknowledgements, right? This is not accumulative acknowledgements. This is one strategy. The other strategy is called explicit retransmission. This is actually what is used a lot. Again, you can either use implicit retransmission or explicit retransmission. In implicit retransmission, what happens? I'll keep, for every frame that I send, I'll wait for an acknowledgement. If I don't get an acknowledgement, I'll repeat or I'll retransmit or I'll resend, right? But this doesn't make a lot of logical sense. So what is actually used in practice is we send accumulative acknowledgements. Just the way we have seen in go back N. We send accumulative acknowledgements just the way we have seen. But in addition to it, there is something called as a negative acknowledgement also that we will send. There is a special type of acknowledgement called as negative acknowledgement. I'll explain you how this works. So the receiver sends something called as a negative acknowledgement frame for every corrupted or missing packet. Okay, this might feel slightly illogical right now, but let me show you, or slightly incomprehensible, because I'm just giving you some theoretical concept here. But you can either use implicit retransmission, wherein for every frame you get an acknowledgement back, right? Or you could have explicit retransmission, wherein you just send accumulative acknowledgements along with negative acknowledgements. In practice, sometimes people try to combine both of them. When you combine both of them, what happens? If there is a good packet, you send an acknowledgement for every packet. For every good packet, you send an acknowledgement. For every bad packet, you send a negative acknowledgement. So people try to use just implicit, just explicit, or a combination of both of them. Okay, all these three are possible in practice, right? Depends on the actual implementation itself. Okay, so what we will look at is, through the rest of this video, we look at explicit retransmission, where we are sending accumulative acknowledgements just like in go back N with negative acknowledgement. Let me explain how this whole thing works. Just give me a second, you will understand this. Imagine I have 4 sequence numbers. Imagine the number of sequence numbers I have is 4, which is 2 power 2, right? 0, 1, 2, 3, 0, 1, 2, 3, so on and so forth. Okay, this is my sender here and this is my receiver. As we discussed earlier, the size of the receiver window is same as the size of the sender window. Let's assume the window size here, the WS is equal to 2. So WR also will be equal to 2, obviously, because my receiver window and sender window have to be of same size in the selective repeat strategy or in the selective repeat protocol. Okay, let's understand how it works. Remember, we are using accumulative acknowledgement with negative acknowledgement. Okay, let me explain how that works. So this is my window. So my sender sends frame 0, cool. Now my receiver is ready to receive anything that is there in this. Look at this, it's ready to receive anything that is there in this window. It received 0, so it received well. So it will tick mark. It will store this in a buffer. Okay, it will store this in a buffer, right? A buffer is nothing but a memory space within the receiver main memory or receiver RAM where it stores all of this, right? So it stores 0, cool. Then it sends 1, cool. I got 0 and 1. I got both the frames that I want in my receiver window. Now, as soon as this happens, I send, look at this. What am I sending here? I'm sending A2, which is an accumulated acknowledgement. Why is it an accumulated acknowledgement? Look at this. I'm not sending one acknowledgement for frame 0, one acknowledgement for frame 1. I'm sending one acknowledgement for both of them. And that's perfectly valid, right? Because as I told you earlier, we are using accumulated acknowledgements. We could have also used one acknowledgement for one packet as part of selective repeat. Any of these strategies is okay. But we'll do something which is more beneficial, which is we know that accumulative acknowledgements are better. That's why we use them in go back N strategy or go back N protocol. So we'll continue to use them. So as soon as my receiver receives 0 and 1, it says, now I'm waiting for frame 2. Now, as soon as it does that, it slides the window. Look at this. It has slided the window, right? Because I've gotten both 0 and 1, I'm going to slide it. All the frames that I'm expecting in the current window, I got them. That's why I've slided it. Cool. And this acknowledgement reaches my sender. Now the sender knows, because it got acknowledgement 2, it knows that frame 0 and frame 1 have been successfully received at the receiver. So it will also slide. It will also slide the frame. Cool. Slide this window, not the frame, sorry. It will slide this window, right? Now it sends 2. Look at this. Now it sends 2. Let's assume 2 is lost. Let's assume 2 is lost in the channel or in the medium. Okay, I have this medium here. Let's assume 2 is lost. Now let's see what happens. So it sends 2, and since 3 is also there in the same window, just like in go back N, it will also send 3. It will also send 3. In go back N, what did it do? In go back N, my receiver would not accept 3. It would discard 3. If you recall, let me show you the diagram. Right, I've shown you. See, look at this. It sent 2, which was lost. Then it sent 3. This 3 was discarded in go back N. Again, remember, this is go back N. In go back N, we discarded it. In selective repeat, the strategy that I'll employ here is this. Is frame 3 there in my current window? Yes, it is there. So which means I can accept frame 3. So I'll store frame 3. I'll store frame 3 in a buffer. I'll store frame 3 and I'll now wait for frame 2. Now remember, I haven't received frame 2, but I've received frame 3. I'm not throwing away frame 3 because we used some bandwidth to actually transport or to transmit frame 3. Why throw it out? Right? I'm going to store it here. I'm going to store frame 3 in a buffer. And I'm going to say, hey, sender, I've already gotten frame 3, but I haven't gotten frame 2. And how do I tell that? I send a negative acknowledgement. Look at this. I'm sending a negative acknowledgement here. When I say a negative acknowledgement, what does it mean? It means I haven't received 2, but I've received something after 2. Very interesting, right? So as soon as, look at this, I'm storing 3. I'm not discarding 3. I'm storing 3 in a buffer. I'm not discarding it. And I've sent a negative acknowledgement. This is what is the explicit retransmission strategy. It's called explicit because we are explicitly telling the sender that there is one packet that is missing. Please resend it. That's why it's called explicit retransmission strategy. In practice, a lot of times we end up using explicit retransmission with negative acknowledgements and accumulated acknowledgements. This is what we tend to use a lot in practice because it is very, very efficient. Now, as soon as the sender receives this, look at this. As soon as the sender receives this, the sender realizes that, hey, there is a problem somewhere. The moment it sees this, it says, okay, problem. See, in this window, look at this. In this window, I have frame 2 and frame 3. The moment I get a negative acknowledgement 2, I realize that, hey, there is some problem. The frame 2 that I sent got lost somewhere. So let's resend it. Okay, again, my window doesn't change. My window stays the same. My window stays the same here. Then it resends frame 2. Now, once I get frame 2, look at this. My window stays the same here. So I received my frame 2 now. As soon as I received my frame 2, I got both frame 2 and frame 3. Which means both the frames that I have in this window, I got them. Which means I will now slide the window. I will slide it to the next 2, which is this. So as soon as the window slides, I send an acknowledgement saying A0. So the moment an acknowledgement 0 is sent, I understand that as soon as this acknowledgement 0 is sent, I know that 2 and 3 have been successfully received by this receiver, and now I can slide it. So it will slide it to 0 and 1. This is how lost frames work, right? Again, here I've talked to you both the cases, right? Here you have the accumulated acknowledgement in the case of good packets, right? This is a simple case. This whole thing is the case of accumulated. So this is your accumulated acknowledgement, right? This is exactly like your go backend. But whenever there is a lost packet, we just use negative acknowledgements asking the sender to resend it. But remember here I need to have additional memory allocated for these buffers to store these packets while I wait for other packets. Right? That's the additional space that I have to allocate for these for the programs that are running on the servers on the sender side and the receiver side. Right? Very simple concept. Now look at this. What happens again? Here your question could be, what happens if you have damaged or lost acknowledgements, right? If you have damaged or lost acknowledgements, then what happens? Just like, again, you have the timeout concept, right? The timeout concept. If you have this will behave exactly like your GBN. In your GBN, what happened? If your acknowledgement arrives before timeout, no need to send. If your acknowledgement arrives after T0, right? After T0, as in after timeout, then you resend. If it arrives after T0, you just resend the frame. You just resend the frame and wait for negative acknowledgements if need be, right? So the concept here stays the same, right? The core concept here itself stays the same. Now let's look at this. So what if, let's take a slightly different take on this, okay? Let's take the case, what happens if you have your acknowledgements which are being lost. So here also, let's take a very interesting example. Let's assume the number of sequence numbers I have is 4, right? Which is equal to 2 power m, right? We know that if I have m bits to represent the sequence number, I can represent 2 power m sequence numbers, right? Now, if you notice, here also we had 4 sequence numbers. We use the window size to be 2. What happens if I use my sender window, which is equal to my receiver window size equals to 3? Is there some problem? Let's see if there is a problem that occurs. Okay. So I have my sender and receiver. My window size here is 3. Look at this. My WS equals to 3. Similarly, my WR is also equals to 3. Cool. Now let's see what happens. Okay. I send 0. The acknowledgement is lost. I send 1. Acknowledgement is lost. I send 2. Acknowledgement is lost. All the 3 acknowledgements are lost. This is the case of lost acknowledgement, right? So when all the acknowledgements are lost, but as far as receiver is concerned, I received frame 0, I received frame 1, I received frame 2. Because I received all the 3 frames in my current window, I will slide the window. Cool. That's how your receiver behaves, right? I received all the frames in my current window, so I slide it. Now look at this. As soon as I send my frame 0, I would start a timer. I would start a timer at my sender, right? I would start a timer here, right? The timer will time out at some point. This is the timeout of frame 0. This is the timeout of frame 0. As soon as it times out and we don't get either a negative acknowledgement or a simple accumulated acknowledgement, I would assume that something went wrong. I would assume that everything was, because I didn't get a negative acknowledgement, I did not even get a proper accumulated acknowledgement. So I would say, since I'm not getting any acknowledgement for any of the frames, neither negative acknowledgement nor accumulated acknowledgement. So I would say, let's resend it. So I would go back and resend frame 0. Now what happens is very interesting. So I send frame 0. Now, see, the sequence number of this frame will be 0. Look at the sequence number of this is 0. Now, as soon as it reaches the receiver says, is there any frame 0 in my current window? Yes, there is a frame 0. There is a frame 0 here. So it will assign this frame 0 that the sender has sent to this frame, to this 0. But ideally, it should have actually assigned it to this 0, because what the sender was sending was the initial frame 0 that it did not get an acknowledgement for. Right? This should ideally be assigned to this 0, not to this 0. But my receiver has erroneously accepted this, thereby messing up the whole sequence of frames. Look at this. This is a problem that you will encounter if your window size is equal to 3. Now look at this. I have 2 power m, which is equal to the number of sequence numbers. 2 power m is equal to the number of sequence numbers, right? So again, what we have proven here is the case where m equals to 2, right? And 2 power m equals to 4. And we said if it is equal to 3, look at this. If my window size equals to 3, things will fail. But if my window size equals to 2, this case will work perfectly all right. So we can show, using the same argument, we can show that the window size, remember the window size in the case of selective repeat, remember, in the case of selective repeat, my window size should be less than equal to 2 power m minus 1. Remember, in your GBN, in your go back n, my window size was less than equal to 2 power m minus 1. This 2 power m minus 1. In the case of selective repeat, my window size is less than equal to 2 power m minus 1 in the exponent. Again, lot of people get confused with this, but this example should help you remember the details, right? In other words, my window size should be less than equal to 2 power m by 2. Right? This is very, very important, right? Again, we have shown a simple example wherein right, that it can't be equal to 2 power m minus 1. What is this? This is 2 power m minus 1, and this will not work. This is equal to 2 power m minus 1 in the exponent. This is working, right? So now we can arrive at the same argument using something that we studied earlier. Look at this. What we studied earlier in the previous video was the minimum number of sequence number needed was the sum of the size of my slide, or sum of my window in the sender side and the receiver side. Look at this. In this case, I'll again prove that mathematically. The minimum number of sequence numbers that we need, we studied this in the previous video, right? The minimum number of sequence numbers that we need is the sum of the size of my sender window and my receiver window. Okay. So now let's see. What does this mean? What does this mean? See, here you have minimum. So, which means this number of sequence numbers is greater than equal to this. Because the minimum value of this, remember, the minimum value of this is equal to this. If the minimum value of the number of sequence numbers, again, this might be sometimes confusing because you have number of sequence numbers. You have number being used twice. So, it's a slight tongue twister there. But the minimum number of sequence numbers you have is this. What does that mean? It means the number of sequence numbers has to be greater than equal to this. So this basically implies this. This basically implies this. Now what is the number of sequence numbers? Number of sequence numbers is nothing but 2 power m if your sequence number uses m bits. Right? So this is greater than equal to ws plus wr. Now we know in selective repeat. In selective repeat, what did we do? We use the same size for my for my r and s, for my receiver and sender. So since ws equals to wr, I can write this as 2 times ws, which means my ws, look at this, what do I get here if I simplify this? I get that ws is less than equal to 2 power m minus 1 in the exponent. This is exactly what I got here also. Look at this, this is exactly what I got here, right? So the general concept that the minimum number of sequence numbers is equal to the size of your sender window and receiver window holds for your selective repeat. This equation holds for selective repeat. It holds for go back n, and it also holds for stop and wait, right? So the simplest way to understand this is the number of sequence numbers is always greater than equal to the size of the sender window and receiver window. If you are confused with this minimum term here, just understanding this equation and using this equation is good enough, right? Very, very simple, but a nice equation nonetheless. Okay. So now let's look at this whole system now. Okay. From a high level viewpoint. Now imagine, so I'm trying to compare all of them. Imagine my size of the sender window, let's assume, is n, right? What is the efficiency now? Look at this. What is the efficiency of stop and wait? In stop and wait, you only send one packet while the capacity is 1 plus 2a. Look at this. These many packets you can send. 1 plus 2a is the capacity. We've already discussed this in the previous videos. While you could send 1 plus 2a packets, you are only sending one packet at a time. Simple. What about GBN? In GBN, if your window size is n, look at this. If your sender window size is n, you will at any point send at most n. You'll send at most n out of 1.2a packets that you can send. And again, the denominator is the capacity. The numerator is the number of packets that you're sending at any time. The same concept holds for selective repeat also. Even for selective repeat, the max that I can send, the capacity is 1 plus 2a. At any point, I'll only send n here, where n is the size of my sender window. Simple. How many buffers do I need here? Look at this. I just need one buffer at the source and one buffer at the destination, or one buffer at sender, one buffer at receiver. Here, what do I need? Here, I need n buffers at the sender and one buffer at the receiver. Look at the buffers that I need here. Let's go back to, where are we? Yeah. So I need buffers to store the data here, right? And I have to keep storing this data here till the time I get the acknowledgement. In go back n, I keep storing them in these buffers, or in buffers are basically nothing but memory locations where I store them. I store them in memory till the time I get an acknowledgement. Only after I get an acknowledgement, I'll move my sliding window and reuse these buffers, right? So I need n buffers here because my window size is n, and I need one buffer at the receiver end. Right? Very simple concept. Okay. So now so what about selective repeat? Selective repeat requires 2n buffers because your window size on the sender end and the receiver end is of size ws, and ws is equal to n here. In this whole table, I'm using n equals to ws. What is the minimum number of sequence numbers here? What is the minimum number of sequence numbers? Just two sequence numbers, 0 and 1 are sufficient. What is the minimum number of sequence numbers here? Look at this. What is the minimum number of sequence numbers do I need here? ws, look at this. ws is the size of my sender window, right? So we have seen this, right? It is ws plus 1. Look at this. We must have shown this here, right? Look at this. ws plus 1 is less than equal to 2 power m. So what does this mean? Look at this. What does this mean? This is the number of sequence numbers. This is the number of sequence numbers. Number of sequence numbers is greater than equal to ws plus 1. Which means the minimum number of sequence numbers is equal to ws plus 1. Right? We have seen this equation earlier, right? So what can I say here? This is equal to n plus 1 because n is equal to ws. In this case, what would it be? Look at this. In this case, we just shown that ws is less than equal to 2 power m minus 1. And what is ws now? Look at this. What is 2 power m? 2 power m is equal to number of sequence numbers. 2 power m is equal to number of sequence numbers. So here you would have 2n here. Here you would have 2n. Right? Very simple, right? ws, look at this. ws by 2 is less than equal to 2m. I just took this. So from this equation, I can write this. ws by 2 is less than equal to the number of sequence numbers. Right? Which means the minimum sequence number that I have here. Look at this. The minimum sequence number, so 2 power m minus 1, right? Which means by 2. So this will become into 2, I'm sorry. So this is 2 into ws. Because this is 2 power m by 2, right? So this is 2 power m by 2. So if I take this 2 on the other side, I get 2 into ws. I'm sorry. Right? That's why I get 2n here, not n by 2. Right? Very simple. Similarly, how many retransmissions can occur here? In this, there is only going to be one retransmission at any point. Right? Here I could have n retransmissions because my window size is n. Look at this. Here my window size is 1, so there is only one retransmission. Here my window size is n, so I could have n retransmissions. Right? Retransmission basically means, we have seen this example here, right? We have solved a problem also, if I recall. Where was this problem? Yeah, we solved this. Look at this. the 567, I retransmitted 567 again. So what is the maximum number of retransmissions? The maximum number of retransmissions is equal to the size of my window, right? And my size of my window was m, is n actually. In this case, if I'm using negative acknowledgement, I only have to retransmit the lost or the damaged packet. So again, this is because of negative acknowledgement. This is because of negative acknowledgement. Now, as far as implementation is concerned, this is the simplest. This is the simplest one to implement. And also the computational power needed for this is the lowest. Very simple to implement. This is moderate. This is slightly more complicated because you have to handle the buffers. You have to handle the n buffers on the sender side. This is the most complex. Even computationally, this is the most involved because you'll have to keep track of the sender buffers, the receiver buffers, and the whole algorithm, the whole complexity of implementation and computational power. If your implementation is harder, in this case, your computational power also required will be higher, right? Because I have to look at this. In the case of my selective repeat, when I get any packet, I have to search within this whole thing and say, oh, this is 3, so I can accept 3. So there is more computational resources required, and even the implementation of it is slightly complex. The computational power needed is also higher. Now, what about bandwidth? This is the slightly tricky thing to get, right? Imagine if I have low bandwidth. In the case when I have low bandwidth, then a stop and wait is good because then my efficiency will be high. Because anyway, I can't place too many packets. Remember, if my bandwidth is low, okay, I can't place too many packets, right? If my bandwidth is low, I can get high efficiency even with stop and wait, right? In this case, I require very high bandwidth. Because my number of retransmissions could be very high, right? For my GBN to work well, I require relatively higher bandwidth than stop and wait and selective repeat. For selective repeat, moderate bandwidth is good enough. Because the number of retransmissions is still fewer, right? So typically what happens here is this, okay? So selective repeat is used in wireless situations because wireless has moderate bandwidth as compared to, for example, let's assume I have some fiber optic cable. Right? Fiber optic cable has very low errors and very high bandwidth. It has very high bandwidth, very low errors. If I have fewer errors, the total number of retransmissions also will reduce, right? It has very few errors. That's why I don't have to retransmit much. So if I'm using fiber optic cable, then my errors are fewer, which means my retransmissions will reduce, and it can also give me a lot of bandwidth, thereby making it very, very ideal to use go back N protocol if you have a fiber optic cable like medium. On the other hand, imagine if I have wireless medium. In wireless medium, my errors could be high. But here, because I have negative acknowledgement, my retransmissions are also fewer. And it is certainly moderate in bandwidth. It's certainly lesser bandwidth than fiber optic. So typically wireless networks tend to use selective repeat. Again, these concepts are so important that we'll re-encounter these concepts again and again. These concepts are not just limited to data link layer. They're foundational concepts on how do you transmit packets or how do you transmit frames in a computer network. They're foundational concepts, right? Again, remember that in terms of computational power, to implement selective repeat, you need slightly more complex hardware and you need more buffers, which means you need more memory also, right? These are all trade-offs. In practice, nowadays, people don't use this much. People use go back N or selective repeat extensively. For fiber optics or for coaxial cables, which have high bandwidth and low error rate, go back N is a very, very good protocol. And it's also simpler, right? Because my buffer size is smaller, my computational complexity is lesser, and it's moderate. Why should I use, see, look at this, the efficiency is the same. The efficiency of selective repeat and go back N is the same. But still I would prefer this because I have high bandwidth. I can get away with smaller amount of memory and my computational resources required are moderate and even the implementation is easier. But selective repeat is often used in wireless networks where where the bandwidth is relatively less than your fiber optic cable like setups, certainly your wireless is certainly good, but it's certainly not as fast as fiber optic today, right? But whenever there is an error, because I'm using negative acknowledgement, my retransmissions are fewer, but I need more RAM, which is not a big problem nowadays. Most computers have decent amount of RAM, right? Or I need more amount of memory to store these buffers. It need not be RAM itself. It could be memory within the network interface card itself. Most modern network interface cards have local memory for all these buffers. It did not store this in the main memory or RAM, right? It actually stores this in the network interface card buffers themselves. And as memory is becoming cheaper, this is not a big problem. But implementation of this is slightly complex and you require more computational power. But that's okay. Most network interface cards have powerful enough computational chips that it can take care of it, right? So that's the trade-off that we are working with.